It was early in 1930 that Besche and Gross GmbH of Germany first used the principle of counterblow forging by having two masses moving against each other. It was realized that the energy of the blow would be used as useful work on the workpiece and not wasted by transmission to the base plate and foundations. This principle saves much material in the hammer base, allows a simpler foundation, and saves capital costs. In the following film, you will see the largest counterblow hammer yet installed in this country. The hammer is known as a DGH-50 model. This means that the tops which meet each other to make the blow weigh over 60 tons each, giving an effective blow of over 60 meter tons. In the works of Fielding and Platt Limited at Gloucester, most of the pieces for this large hammer were machined and sub-assembled. The hammer was designed by Besche and Gross GmbH in Germany, who have licensed Burton Griffiths and Company Limited to manufacture in Great Britain. It was Burton Griffiths and Company Limited who entrusted Fielding and Platt with the machining and building of this hammer for their customer Ambrose Shardlow Limited of Sheffield. On this DGH-50 hammer, the tops are coupled together by hydraulic cylinders and rams, as opposed to steel bands on the smaller types of hammers. Here, the whole base plate assembly is being erected in the Fielding fitting shops, together with the hydraulic cylinders, rams and coupling pipes, prior to final erection at site. While the hammer is being made and machined at Gloucester, the foundations are under construction at Ambrose Shardlow's works in Sheffield. The foundations involve excavating to a depth of 26 feet below floor level and casting 1,800 tons of ferro-concrete. This is very much less than would be required for a conventional hammer of equivalent capacity. At last, site building can start with the arrival of the base plate of 28 tons. This is lowered into the foundations and accurately leveled up. At all times, a skilled erector from Fieldings supervised the building operation. The foundation bolts, each 8 feet long, were then grouted in. Each 65-ton side frame was jacked and manhandled down the pit and into position, as large mobile cranes were unable to maneuver within the hammer area. The total weight of the hammer is approximately 340 tons. Its height above ground level is 22 feet, and the floor of the pit is 24 feet below ground level. To keep up with the capacity of a hammer of this size, an oil-fired furnace had to be purchased in order to utilize the full potential of such a machine. Also, a special 2-ton diesel-driven manipulator was necessary, as billets can weigh up to 3,500 hundredweight. A 4-column downstroking trimming press of 3,000 tons power was supplied by Burton Griffiths and built to Erie foundry designs by Fielding and Platt. This is used to clip or trim the flash from the die line of the forging. Such is the size of the forging that at times very nearly the full power of 3,000 tons is used to clip away the flash. The press itself is self-contained with a direct-driven high-speed oil pump. The hammer is so designed that dies of overall length of 12 foot 6 inches can be accommodated on the die notches at the tops, and the total weight of each die can be as high as 14 tons. In this particular crankshaft, a batch of forgings are first roughed out on roughing dies and then finished on accurate finishing dies. Servo control between the hand lever driving the hammer and the air inlet and exhaust valves enables the driver to have very sensitive control of both the power and movement of the tops, in spite of the combined weight of 150 tons in the parts which are being moved. Power for the hammer is supplied by compressed air at 100 pounds per square inch through an inflagrator air heater. This gives 45% compressed air economy. The air consumption under working conditions is 85 cubic feet per blow of hot air at 250 degrees centigrade, compared with 145 cubic feet per blow of air at 160 degrees centigrade. Figures which show clearly the economy of such a hammer using heated air. Sawdust is thrown between the top and the forging to remove the scale and also to free the forging from sticking in the top die. Finally, the sawdust is added into the bottom die to clean the underside of the forging of scale before it is removed. This particular forging is for the crankshaft of a large diesel engine for railway locomotives, now made in this country by Bristol Siddeley Engines Limited. course, after forging, there are many operations such as machining, inspection, balancing and crack detecting, all of which have to be performed and all of which are of very high precision before any crankshaft or forging is fit for use. Having now seen this machine at work and its end product, one cannot but admire the foresight of Ambrose Shardlow Limited, who ordered it, the German designers who designed it, and the many British engineers who have built this giant of all forging hammers.